Okay, so today we've talked about spectral methods last couple days. Two lectures ago on Monday, I guess we talked about doing FFTs. Talked about the basic idea behind the FFT. Then we're now talking about. Then last time we talked about Chebyshev. Now we're going to talk about spectral implementation. So partly what we're going to do is code up in class. Okay. So let's consider the general idea first, which is that a PDE where L is some linear operator. You know, for instance, L could be something like this. You know, you're taking two derivatives of the function in x and plus some constant times first derivative plus c. The main thing about this is it's constant coefficient, linear. Okay? Nu is everything else that's bad. What I mean by bad is nonlinear terms, non-constant coefficients. Let's talk about how to deal with them. Okay, so Nu is going to be stuff like u cubed plus some f of x, u. Okay? These are just examples. Now, when we want to solve this with a Fourier transform, the whole idea is just to run it through an FFT algorithm. And what's going to happen with that? When you do this, notice what happens. You can FFT both sides, and on the left then you get that, u prime t, and on the right you get Fourier transform of this L of u. Well, what is a Fourier transform of L of u? Well, you have this structure in there, right? You're Fourier transforming the whole thing. And what you know is Fourier transform of derivatives pop out in IK. Okay? So here's two derivatives. It pops out IK. That whole thing's squared. Well, IK squared is minus k squared. So this becomes minus a k squared u hat. Plus, take the Fourier transform of this term, one derivative, just pops out in IK, plus I, k, b, u hat, plus c, u hat. The bottom line about this operator L, which is the linear part, constant coefficient, is that this thing here all turns out to be, I can collect all these terms together into one expression, which is a function of k, and I'm going to call that alpha k. So basically the LU just turns out to be some function of k times u hat. Plus, well, the nonlinear term, you just got to run it through your transform. But now that you've transformed it, you can throw it through ODE45. It's now a big system of ODEs for all the Fourier modes that evolve in time. Okay? So, how do you handle solving some of these things? Okay? So for instance, let's talk about then specifically this term here, because when you solve these problems, you've got to figure out how to handle these nonlinear terms. So I'm going to give some examples of how to handle these things. Suppose n is equal to something like this, f of x du dx. I want to Fourier transform this thing. Okay? Well, that's easy to do, right? But notice, before I Fourier transform it, I have to know what the derivative is. So to calculate the Fourier transform of this thing, there's a couple steps. First, what's du dx? Well, how do you calculate the derivative? Well, you know that the derivative, Fourier transform of the derivative, is equal to ik times transform of the function. So you say, oh, okay, well, if I want to know what du dx is I can then say, well, if the Fourier transform is this, du dx then is simply the inverse Fourier transform of ik times u. Okay? So this here inverses this both sides, so you get back to du dx. So this is du dx. Now once you have du dx, then you can say, okay, take this du dx, multiply by your f of x, and then you f of t, that whole thing. Now you're ready to actually calculate that term. Okay? Everybody good with that? What about a nonlinear term like what I wrote over there, which is u cubed? Well, this is really easy. All you've got to do is f of t, u cubed. You're done. So nonlinear terms are fairly easy objects to handle. Then I give one more example. But this is the basic idea behind doing the Fourier transform. For actually implementation purposes, the thing you really worry about taking care of, frankly, is this term right there. All this other stuff here, you just say, well, how many derivatives do I have in front of this stuff? You know, if it's two derivatives, I pop out an ik squared. If it's one derivative, it's ik. That's fairly straightforward. This stuff here is a little bit harder to deal with. Okay? Now, what we're going to attempt to program in class today is the problem you're doing for the homework. But now for the homework for problem 2, right, and the homework is that you're going to do it all with these finite difference methods, essentially, except when you solve the stream function. The stream function you're actually solving with Fourier transforms, right? Okay, well, what we're going to do now is solve the whole problem spectrally. Okay, so we're going to do FFT, the whole thing. So let's write down the problem, and then we'll start building up what we need. And we'll see if we get it done by the end of class. But at least the structure will be there, and that's important. Okay? And I'm going to change the program from what's actually in the notes a little bit, because I've got better program now, or better ideas for it. But I haven't really actually seen if they work. And we're going to go for it and then just see what happens, okay? So we might not have a working code by the end of the day, but it's on the right track. All right, so here's what we have for the homework. Is it this? That's close to that, right? All right. So, and really what that comes out to be is something like this. And then you know, I don't know, I can't remember if the signs are right here, but if it's a wrong sign, it's going to spin the other way. We can always fix it later, with this relationship still holding. Okay? This is what we want to program in. Now notice, we have x derivatives, y derivatives, two derivatives in x and y, two derivatives in x and y. Okay? So we need to start thinking about how to build this thing. And we're going to do it all Fourier transform-wise. So when you Fourier transform this whole equation, okay, let's talk about this equation here. Then you Fourier transform it, you're going to get Fourier transform of omega is equal to Fourier transform. This is two derivatives in x, two derivatives in y. So that's going to pop out something like a minus right? Kx squared, ky squared. That's the two derivatives in x, two derivatives in y. Now remember, kx squared goes in this direction, ky squared goes in that direction. We have to keep that in mind when we actually solve the problem. And then, these other terms. These are the nonlinear terms. Non-constant coefficient, I guess. And here, we actually have to just calculate these things and then Fourier transform them. So it's a lot like this case here. We have an f of x, we have a du dx. First we have to calculate the derivative and the function of f of x. Then once we do that, we can put them together, then FFT it. Or inverse FFT it. Okay? All right. So that's the basic structure. So let's start off. Simple, build up. Come on. There we go. Put the brightness on max. Let's see if you can see that. Okay. All right. Here we go. Start off with my favorite commands. Clear all, close all. It's always a good way to start a code. Okay. You guys have all tried that. You guys all have that in your top of your codes, right? Okay. All right. So first of all, let's put in some parameters like new, which, by the way, is the same as mu in the homework, so if you haven't figured that out. Let's make it small, like I've suggested. Let's now set up a spatial domain. My L values are going to be 20 in y and 20 in x. I have to give the number Fourier modes in x, or Fourier modes in y. And when we break this problem up, remember now what we're doing, we're setting up a domain that's broken up to points this way. These are my n of x, points this way. These are n of y. Remember that when we send this into OD45, we have to send in a big vector. So we're going to reshape this thing, right? Omega is all these points on here. But when we send it on OD45, we have to reshape it by stacking them up. And this vector is of length n of x times n of y. Okay, that's the length of it. So I call that variable big N, which is n of x times n of y. Okay? Now once we've got that set up, we define our spatial domain. x2 is a linear space between negative Lx to, we're going to go from Lx over 2 to Lx over 2 in n of x plus 1 points. Remember, I call this x2 because it's going through these points. There's n plus 1 points total, but the last point's periodic boundary, the last point's the same as the first. So really all I care about is the first 1 to nx of these things. Notice I can drop off that last point because it's the same as the first point. Okay? Now we copy this and we make a y in here. Do the same thing for the y variable, which is y, y, y. Okay? So now we've got our discretizations. So all this is the preliminary setup, just defining our domain, defining the cutting up of this domain. And that's it. All right. So now we're going to define initial conditions. Now, I didn't even bring finger puppets today to help out with entertainment. Should have done that. I was trying to save it like, maybe every other time I do it now, but maybe I need the gimmick every time. Okay. Initial conditions. Plus, I got to find some new celebrities to show up. I can't keep recycling these ones year after year. Let's now make this thing on this box. Right now, x and y, we know it to represent these two directions, but the computer doesn't know that yet. So let's tell the computer to do this. X and y are now going to be on a mesh grid, x and y. So now, big X and big Y have directional sense. Big X knows that it's the x-axis, big Y knows it's the y-axis. Okay? That being established, we are basically ready to define some initial vorticity. It's called omega. And I don't know, I came up with, we're going to do a stretched Gaussian here, so it looks elliptical. And just to not go any further, but to just see what it would look like, let's go ahead and plot this thing right now. Okay? And I like to use some things like shading and terp, color bar, draw now. By the way, the draw now command is a nice one because oftentimes you'll have code below here. And I don't know if you've seen this, but like you'll run in your code and it has a bunch of stuff. It'll pop this figure up on your screen, but won't actually plot the data. Not until the very end of the code. The reason it does that is because it's going, okay, it will actually flush the screen up, but it won't actually throw the data out there. Just keep running and saying, just hold on, I'll get it to you eventually. And it'll run through your whole code and before it gives you a figure. The draw now command says, no, actually, give it to me right now. When you're right here, you flush the data up to the screen, to the buffer. Then you can continue on. And that's actually nice. Okay? All right. So here we go. Ready? Let's run this. Yeah. Save. And that is weird. I'm not sure what's going on here. Sorry. Okay. All right, well, we're not going to plot it. Sorry. It would look really cool if we did. Somehow, it's not even killing the screen. Something's a little bit screwed up here. There's no error message. It's just locked up my. Okay. Yeah. No. Let's just. No, there's something wrong with. I think sometimes the people haven't worked on the Mac version of MATLAB very well yet for some figuring plotting issues sometimes, and sometimes they'll just lock it up, and so I'm locked up right now. But not to waste time, we'll just keep going on, and then you can code this later. Okay. All right. So, continuing on. We have some initial data. That initial data is what we're going to throw in here. But remember, when we solve this, this is now a differential equation in omega hat. In other words, the Fourier transform. So our initial data we're throwing in is actually the vorticity in the transform domain. That's our initial data. Okay? You don't throw in omega, you throw them in. You're solving this set of equations here. And this set of ODEs is for omega hat. So it needs initial condition in omega hat. Okay? So, this is what we want. We want the Fourier transform of this, so you just FFT2 it. There. Simple as that. And, in addition, we're going to have to stack this thing up, right? So, that's easy enough to do. And when you stack it up, let me see where my page 95 is. We want to reshape this thing. Let's call it WT2. So the WT will be, that's vorticity transform. So omega transform. WT2 will be the transform. The 2 will represent that it's stacked data. Okay? So you want to reshape this thing. You want to reshape this transform variables out into a n by 1. N rows, 1 column. Or 1 by n. It doesn't matter, really. But either way, you can either stack them this horizontally or vertically. I choose vertically. Okay? So we're ready with our initial conditions. And so now the question is, what do I do with this? Well, now I'm just basically ready to throw this in to the code to solve. All right? So now we're going to take this, throw it in here. The last thing we need here, though, however, is these kx and ky's, right? Because the kx and ky's are going to allow us to take the derivatives. Okay. So let's come back up here after we've defined these domains here. Let's define our wave vectors. Remember, it's on a 2-pi periodic domain. So, for instance, you scale it down to 2-pi over L of x times like that. And we did this in class earlier. Oops. So, this now sets up a vector of the k wave numbers, where remember we've shifted it because the FFT does this shifting property. So we've taken the cat into account here. We've scaled it down to a 2-pi periodic domain. And finally, we rewrite the first component. The first component of this thing was 0. Now remember, when we solve for the stream function, here, you have a divide by 0 problem if you leave that as a 0. To avoid the divide by 0 problem, all we have to do is come over here and make that thing something small, 10 to the minus 6, for instance, and that's what we're doing here in the code. So by making this thing 10 to the minus 6, essentially what we're doing is taking out any possibility of a division by 0. Great. ky is pretty similarly defined. Oops, 0, and then n of y over 2 minus 1, and then minus n of y over 2 to negative 1, and then ky1 is equal to 10 to the minus 6 again. Now, again, kx and ky do not have a directional sense yet. Okay? So to give them a sense of direction, we say, we use the mesh grid command. Kx, we'll call it capital Kx, ky is equal to mesh grid, Kx, ky. It now knows from this command that Kx is in the x direction, ky is in the y direction. Now these are matrices that we get out of here, and we can use them for what we want to do. Now one of the things that we are going to use often, or twice, 2 derivatives in x, 2 derivatives in y, 2 derivatives in x, 2 derivatives in y, which both give you this kind of structure here. Kx squared plus ky squared. So this is a big thing. So I'm going to make a new matrix that basically just does this. 2 derivatives in x, 2 derivatives in y. Because that way we don't have to keep calculating this out. So let's call it k derv is equal to kx squared plus ky squared. Okay? That's it. Now you are ready to actually send this thing over to your differential equation solver. Okay? Solve the ODEs. So you're solving a PDE, but you've broken this down now into a bunch of ODEs by discretizing it. So how do we solve it? Simple. I call it TWSOL. So in other words, WSOL is my omega solution. I don't know, you can call it whatever you want, but we'll call OD45, and we'll call some, I've called the spec right-hand side for the spectral right-hand side. It's going to call the right-hand side function. We are going to give it t-span here, the time span. And the time span, we could do something like 0, and I just want to see it at time 0 to time 10 in steps of a half. Okay? We give it time span and my initial condition, which is WT2. This is a Fourier transformed initial vorticity, reshaped. Okay? Here's a space for options. which I'm not going to play with the tolerances. And then what are the kind of things I need in this right-hand side? Well, let's look at over here. First, I need to be able to take this derivative, and I've defined a vector k-derv, or matrix k-derv, that does this operation, so we should send that in. I also need to calculate single derivatives in y and x, which means I need my k of x and k of y in there. So I need to send in 3 matrices, k-derv, kx, ky. I need my mu value to go in there as well. And that's it. I'm going to calculate my stream function inside of my right-hand side. Okay? So all I need to do is send in the vorticity. That's it. Everything else is going to happen on the right-hand side. And then when I come out, that's when I have to begin the process of extracting things out. Okay. So I need to send in here k-derv, kx, ky, and mu. Let me see. Do we send those out? Yeah, mu. Nu. Not mu. Nu. You'll bring me a newt. Did you get the reference? No. No, you must cut down the tallest tree in the forest. No. I turn me into a newt. Just bring me a shrubbery. That's what you must bring me. You guys don't know that reference? You don't know? Holy Grail? You must cut down the biggest tree in the forest with a herring. No? Doesn't ring a bell? Your homework before the end of this term, or you fail this class, to watch Monty Python's Holy Grail. If you choose not to do so, don't even bother turning in a final report. Okay? You must give at least one quote in your final report from that movie. God, that is so sad. You guys are so uneducated. Youth this days, what are they? What are they? They're not learning anything. Man. Okay. Anyway. Figure out your quote. Ask your friends. They must know. And if they don't know, make them watch the movie with you. Okay? All right. So everybody cool with this so far? We send it all in. And why don't we actually, let's assume that we solve it correctly. Let's post-process it right now. And then we'll go right to the right-hand side. So what this is going to do, it's going to go in here. It's going to crank away on the set of equations. What's going to come out here is time and the solution. And in fact, I'm not going to call this WSOL. I'm going to call it WTSOL because this is the transform of the solution. In fact, I'm not calling it WT. I'm going to call it WT2SOL because it's not only transform, but it's the stacked transform. Right? So this thing T is a column vector. It reads down the times that it solved for. And every column of this is the actual, how many columns of this are there? There are big N of them. Every row of this vector, it's going to be a huge thing. Every row is the solution at time 0, time a half, time 1, time 1.5. And this thing is N components. So what you need to do is take that thing, reshape it back, inverse Fourier transform it, then you have the vorticity at a slice of time. Okay? So, for instance, let's go ahead and look at this thing. Let's make a little thing that just plots it. So for j is 1 to length t. So what we're going to do is just going to run through a thing, and we're going to plot each slice and then pause it, and then you can hit the space button, and it will plot the next slice. Okay? So what you're going to do, the thing you need to do is you need to grab the jth row of this thing. So let's call that my W2T is equal to. I grab the jth row. Once I have this jth row, what I want to do is I want to reshape this thing back to an n of x by n of y matrix. Once I've reshaped it, I want to inverse Fourier transform it back to this real space that we're working with. Okay? So there we go. I've grabbed a certain row, I've reshaped it, I've inverse Fourier transformed it. Now I have the vorticity at, you know, wherever I am at this certain time. I'm going down this time vector, and for that time, I'm grabbing that vorticity slice. And then from here, you could say something like, you know, okay, plot this thing. You could plot it as a function of your x and y. There you go. And then you can say just pause. And what will happen now, it's going to plot it, and then until you hit a button, it'll just hold that picture. And then you can hit the space button, and it'll show you these different plots in time. Now there's one problem with this at this point, which is when you do this, when you inverse Fourier transform, for instance, all the data here should be real. When we come to solve this equation here, this should all be real. But what's the problem? I'm using the inverse Fourier transform and the Fourier transform. The Fourier transform has an e to the I stuff in it. Now what you know is you have numerical round-off in this problem. So even though the solution is real, there are no imaginary components, when you actually FFT it, there is numerical round-off, which says, well, actually, you pick up an imaginary component, and it's like 10 to the minus 16th. It's on numerical round-off level. So when you do this, your solution really is real, but computationally now it has this round-off in the imaginary axis of data. So when you come over to here to do something like this, where you're plotting it, you say p color x, y, omega, it's going, well, this is actually a complex quantity. Because there's some imaginary components that are like 10 to the minus 16th. So all you have to do, when you inverse Fourier transform, you say, put real right there. So you take the real part of the inverse Fourier transform, kills off all the imaginary components that were only due to round off anyway. Okay? We've just post-processed the data. So this is our basic structure of the code. All the action of solving the code now is going to happen in this right-hand side. So everybody's happy so far? So remember, when you solve this thing, you're solving it completely in the Fourier domain, and then you're bringing it back out. And then you have to remember that your data is in the Fourier domain, and you have to inverse Fourier transform it to get back to what you need. Okay, so now the big part is to write the code for spec right-hand side. Let's save this. So, file, new M file. File. Huh. It's not allowing me to open a file here. Okay, something screwed up on my computer. So here we go. Here's our new file. If you return high enough, it'll serve the purpose what we need. Function. We need to now calculate the right-hand side of this set of ODEs. We need to calculate this thing here. Okay? So I'm going to call this thing RHS for right-hand side. And you need all these constitutive components where, for psi, I need to solve this thing. Now remember what we did in class. We actually solved for this. We're given the vorticity, right? And we found that this thing basically resulted in the Fourier transform in x and y was equal to minus Fourier transform x and y of the vorticity divided by, right? That's what we found. That's what we actually did this in class earlier. And you're actually doing it in your homework too. So we need to do that, and then we could start thinking about calculating these pieces. So the right-hand side is going to be this function spec RHS. And what's coming in is our t-span. Our initial condition, WT2, remember, it's the vorticity transform stacked. The 2 stands for stacked. Okay. Dummy, that's our tolerance stuff, and we don't want to do anything with it. And then I'm sending in, how many things am I sending in? kderv, kx, ky, and new. Okay? We've got everything we need. Now, the first thing you need to do when you get into the Fourier transform domain is you've got to actually calculate this stuff. Look what you need. You need to calculate the vorticity, stream function, which means you need the vorticity, FFT of the vorticity. But now, this is not the stacked vorticity, but the regular vorticity. And then if you want to calculate omega x and omega y over here, you're going to actually need to know what the vorticity is so you can multiply by IK. So the first thing you want to do when you get in here is say, okay, what is the vorticity? Well, what I have to do is my WT, right, is going to be the reshape of WT2 back to that. So I've reshaped it back out. And then I also need my vorticity, which is the inverse Fourier transform of WT. So what I've just calculated is now what I have is back in the regular domain, I have the vorticity, it's transformed in this two-dimensional picture, and the vorticity, it's just the vorticity itself. The vorticity and its transform both now in 2 dimensions. Now I can calculate everything else. What's the stream function? Check it out, one-liner. I love doing this with just one line. Right here, right? This is the stream function. All right. So the stream function, talk about this, it's minus Fourier transform of the vorticity, K derv on the bottom. That quantity right there is Fourier transform of the stream function. So all I have to do to get the psi is do that. I inverse Fourier transform the transform of the vorticity divided by K derv. The dot's very important. You need the dot there because this is a matrix, that's a matrix. That's as simple as your code needs to be for your homework too. Except instead of having WT here, which we're getting from what's coming in, you would just say FFT2 of omega. So that's your one line for solving for the stream function with FFT method. Isn't that awesome? Anyway, I think that's pretty awesome. When you really get good at MATLAB programming, you can write these incredible amount of codes just so condensed. One of the differences I've found with MATLAB programming now versus what used to be like Fortran or C programming is that when you used to program in Fortran and C, you'd have to actually write a lot of this stuff out and do every piece separately. But now with the program functionality of MATLAB, I can take a code in Fortran that I took this long to write, and I can pretty much compress it to almost that. It's really amazing. So it's really terse code, but has everything you need there. Okay. We now have the stream function. We now have the vorticity. Now we need to calculate. What do we need to calculate? Now we need to calculate all these components. So first of all, if I want to take the Fourier transform of this stuff here, I need to know what omega y is. And I need to know what psi of x is. And I need to know what psi of y is. And I need to know what omega x is. Well, how do I calculate omega y? Let's start with something like that. Omega y. What is it? Well, how do we calculate derivatives? Let's look over here. If you want to calculate a derivative of a function, what you know is Fourier transform of the derivative is IK times the transform of the thing itself. And so if you want to find the derivative, you just inverse Fourier transform this IK times the transform of the function. So all I need to calculate the derivative in y or x is to say omega y is just going to be the inverse Fourier transform, remember in 2 dimensions, of I times ky dot times, that's it. I'm calculating the y derivative. That means I need my IKY to come out, times Fourier transform of the function itself, and then inverse Fourier transform it. Simple as that. How would you calculate your psi y? Same way. IFFT2 of I times ky dot times wt. You do the same thing here with omega x is IFFT2 of I times now kx times t. Psi of x is equal to IFFT2 of I times kx times. Oh, sorry. Not, these are not supposed to be omega t. These are supposed to be psi of t's. What is the Fourier transform of psi? Well, you just go FFT2 of psi. Okay, that's it. I now have omega y, psi y, omega x, psi of x. We are ready to calculate now the whole right-hand side. All we have to do now is add these terms up. The right-hand side is equal to, then, nu times. What do I have? Oh, so it's negative nu times. This is my k deriv times Fourier transform omega. Okay, so it's minus nu times k deriv times omega. That takes care of this term. Minus this term plus that term. Minus this term, well, this is the transform of psi of x times omega y. So, minus the transform of psi of x dot times omega y. Plus this term here, which is plus FFT2 of psi y dot times omega x. And that is all you need. 6 minutes to spare. Plus I talked about all that stuff. This is the code for solving this thing completely spectrally. It's really amazingly compact for what we're actually doing. And the thing to keep in mind, this now is spectrally accurate. This kind of code here, I've had you do it with the finite difference method. But one of the things you'll notice with the finite difference method, with your vorticity, is you'll notice some choppiness when you start seeing your swirling. You know it's supposed to sort of look something like this. And wherever this, you start seeing some choppiness here, because basically that's due to the fact that you probably have resolution issues, not taking enough points this way or this way. Okay? So your accuracy is actually a lot less. It's finite difference accuracy. You're using second order finite difference versus when you do this spectrally, you're having spectral accuracy. So your ability to resolve this with the same number of points is going to increase significantly. Okay? That's one issue. Second, when you're solving this stream function solve here, if you haven't done so already and looked at your code, you find that if you do this, if you solve the problem with the stream function solve, like this with an FFT versus LU, A\b, whatever, this is the fastest thing you've got. It's n log n. LU is the second fastest at order n squared, and there's a big difference in your code time. Okay? So, this is a nice example code. We're not going to be able to run it, thank God, because in some sense I can boast right now. I think it's awesome. This code just is, everything works. Because probably, if we ran it, there'd be little bugs here and there, and we'd have to fix them up. But the point is, here's the general structure. And if you understand this code, if you go through line by line, there's not that many lines there, really. There's a lot of setup. I want to actually point this out to you. Let me compactify this a little bit here. Your whole right-hand side function, 5 lines. 5 lines you need to understand. All this stuff up here at the beginning of the code, well, look what you got. Well, that's just, that's stuff that you don't need. All this stuff here, this whole area, is just simple setup. Just defining things, breaking it. You're not doing anything mathy there, right? There's no algorithm there. It's just generating initial conditions and defining your L space and your Y space, breaking them up. Nothing there. This here, this part of the code is just simply extracting the data and plotting it. So really, the bulk of your code sits right there in 5 lines. If you can understand those 5 lines of code, and you really understand what's going on with them, for instance, the last homework will just be a breeze for you. Because the last homework, we're going to do not this problem, but we're going to do a couple set of PDEs. But we're going to do it all spectrally. And basically, if you understand this, it's just a matter of taking this thing, generalizing to that set of equations, you're done. I mean, it's really that fast. Okay? 5 lines. Plus your quote. Don't forget your quote. Like I said, don't even bother turning something in. If I don't see a quote in there, you write that down. Okay? And there are many quotable things in the Holy Grail. And the fact that you haven't seen them is just, I can't believe they let you get a college degree, an undergrad degree, without seeing that. But, oh well. Okay. On? Okay. Office hours today, just in case you guys are watching and you actually see this before office hours. I have a PhD committee exam at 1 p.m. today, and that's probably going to go to 3. So what I'm going to do is office hours will be 3 to 4, and then from 4 to 5 I have my other office hours, but 3 to 4 I'll be in the office and you guys can come by. Okay, and I'll try to extend my office hours a little bit more next week, and then we'll do a due date, which is a week later. So in addition. Okay.